So the next type of configuration we're going to look at is a differentiator. And so we see the differentiator is actually just the integrator where we've switched the positions of our resistor and capacitor. So overall, same general components. So let's go ahead and analyze this, starting with our ideal op-amp properties. So we know for an ideal op-amp we have zero current going into our input terminals, and we know that we also have zero differential voltage between the input terminals. So since our non-inverting terminal is at ground potential, that means our inverting terminal is also going to be at ground potential, and we could say that it is at a virtual ground. Okay, so just like we did last time, in order to help with the analysis, I can define some currents and voltages for my resistor and capacitor. So I can say over here we have a current IC going through my capacitor. We have a current VC across the capacitor. Over here I have a current IR that is going through my resistor and a voltage VR across my resistor. Just like with the previous videos, I've defined it such that the reference currents are going through a voltage drop, meaning that we just use a positive sign for any IV equation. Okay, so what we're going to do pretty much the same steps as we did with the integrator. So we're going to start with KCL. We see we have IC and IR both going into that node, nothing coming out. Of course, we can rearrange that to be IC equals negative IR. From there, what we're going to want to do is to use our IV equations. And so remember, for our resistor, that's just Ohm's law. But for our capacitor, we said that I equals C dV dt. Okay, so for our capacitor, we can plug that in. We have that IC is equal to C dVC dt, because VC is the voltage across the capacitor. We know that's equal to negative, where that negative sign is just following along from the previous line. From Ohm's law, IR is V sub R divided by R. Okay, but because we said this is an ideal op-amp, zero differential input voltage, our inverting terminal is a virtual ground, we can see that our VC is actually equal to VI, and we can see that our VR is actually equal to V out. So if we update that, we can say this is C dVi with respect to time is equal to negative V out divided by R. So all we have to do here is we just have to multiply this negative R by both sides to get that our output voltage is equal to negative RC times the derivative of our input voltage with respect to time. And so here we see that our output, as promised, is proportional to the derivative of our input signal. One thing to note is that typically these differentiators are not used in practice because they are going to be more susceptible to noise than other types of circuits, for instance, like our integrator. So susceptible to noise in the input. And so the reason for that is maybe we have some really small amount of noise, so it's a small noise signal, so maybe in our integrator that doesn't really get picked up. But maybe if we look at some section here, and maybe we're going to blow that up and look at it a little closer, what we might see is that really we have spaces here where this is changing really rapidly. So across any given stretch here, the derivative might be very high. So of course, if the derivative is very high from the noise, then we're going to get a very high value here, which is going to lead to some non-negligible value in our output. And so if that's coming just from a noise, we don't want that. We want our output to be just due to the signal and not to noise. One way that we can sort of relieve or alleviate that is by putting a resistor in series with this input capacitor. But even by doing that, we still have to be careful when we use these differentiators.